Okay. Okay. So let's start again. So welcome to the sports data analysis and visualization tutorial. My name is Romain Vimot. I come from France, and as you can see, it's I'm in a building surrounded by sports fields and sports equipment, so it's completely on topic. Unfortunately, today the team of Lyon, which is my home team, got defeated. But hopefully tomorrow, Benzema, who is from Lyon, so he got his most of his training here in Lyon. He might get the Ballon d'Or tomorrow. So today's playing for Real Madrid, and we know if he will get the Ballon d'Or tomorrow or not. So today we're going to talk about so sports data visualization, but in a more practical way, more applied way than we usually do it in research. The tutorial is split in two parts. The first part is going to get about the design space and examples and data sets, which is probably the most important thing when you work on sports data visualization. And the second part would be about coding. We'll get to a live visualization of public sports data. So as I said, I'm from France, Lyon. I work for as an assistant professor for an engineering school. I've been working on sports data for probably more than 10 years now. I got started in 2012 when I was a postdoc at INRIA. At that time, I was working with Jean-Daniel Fekete and Charles Perrin on event data, basically events that were happening around the board. And even though you might think it's not super complete data set, at that time it was already very novel to get this type of data. And we, in particular, we designed this soccer stories visualization. Then I moved to a more finer grain data sets, basketball data sets from the NBA, which were collected with high-speed cameras, and I'm going to talk a little bit about it after. And then I work more on pitch control visualizations. And since 3 to 4 years now, I work on getting my own data using computer visions, which takes a lot of time, and it's a different field because I realized that to do good visualization, or at least novel visualizations, you really need to get good or very good data. And also I got interested into more niche visualizations, niche sports like table tennis and swimming, which are usually not covered that much on TV, or at least you don't have lots of public data sets. So the goal of this tutorial is, as I said at the beginning, is to have a very applied, practical approach. We're going to get to build those types of visualizations using public sports data, like this pitch control visualization. I'm going to talk a bit about the design space of the sports visualization. So I won't cover all the types of sports visualization. It's a very, very broad topic. There has been states of the art, and if you attend the Viz session on, I guess, on Thursday, you'll get a broader overview of the design space. I will actually focus more on spatial visualization, like visualizations that use like a space representation, because I think that's a very interesting way to provide context to the game events. We talk about the technical steps, and as I said, we do some live coding. What I won't cover during this tutorial is the design space, the design process. So basically everything that's before getting the data, the research questions, the goals. We start with the data. I won't talk about the sport-specific statistics. I try to remain sport agnostic, and I won't talk about historical or predictive visualization. If you want to know more about the recent advances in sports data visualization, so there is this session on Thursday, or you can use this very nice visualization made by Hendrik Strobelt and Benjamin Hoover that basically gives you an overview of all these papers. And you have this nice island, which is called the Sports Paper Island, and where you can easily find all the sports, where I grouped all the sports papers. So if you use the tool, it's interactive, and you hover this island, you get all the recent sports visualization. And if you want to get a broader overview of the field, we wrote this nice state-of-the-art paper a couple of years ago. So what are the motivations and main examples of sports visualization? So first, what is sport? Sport is an activity that involves physical skills in which an individual team competes against another or others for entertainment. This is one possible definition. And what's important is that the visualization reflects this physical activity. That's the main goal. Then there are additional goals that are to convey the spatial constraint. Your visualizations need to show what are the pitch limits, what's the route, if it's a linear sports where there is a ranking. You might also take into account the rules that regulate the plays, the use of the ball and accessories, because sometimes it's a part of the strategy, how the players handle their rackets and what the type of shots they can do. So this is something that you may include in your visualization. And also you may also take into account the schedules, the games, the tournaments, because you might want to if you want to show the big picture of a tournament, that's the structure you need to get, and that you don't have in like tracking data or event data. So those are additional data that were actually called in our state-of-the-art, we call that metadata. So those are additional information you need to describe the context of the game. Now back to the sports data. Usually you have two types of data. Here is a sample of sports data. So you have different ways to organize them. You can organize them more vertically, horizontally. I'm not going to talk about it, even though it's a big problem because everybody uses their own data format. But when you start exploring sports data, what's important is to identify the events that occur. For instance, in soccer, it might be a shot, maybe a goal, and tracking data, basically positions of players. And we'll see later that, unfortunately, in sports data set, either you have good events, it's complete, or you have good tracking data, but unfortunately, you don't necessarily have both. Before talking about more technical aspects, I'm gonna give you some of my thoughts on why you should get into sports data. So of course, if you're in this room, you're already convinced it's an interesting topic. But I want to emphasize and it might give you some ways to explain to others that it's actually worth of interest. So first, it's enjoyable. Like if everybody has a favorite sports team. Most of people practice sport, so I think everybody relates to sport and enjoy watching sport. Even though we might like sport and practice it, working on sports data visualization or analysis or whatever, it may give you more objective way to look at sports. Even though you are very familiar to the sports, you are even though you are elite athletes, at least looking at the data, it gives you more objective arguments to explain your performance or to convince others to practice them, to do some things in another way. Also, when you work on sports data, you really address difficult challenges. I realized that even though everybody might understand the end results, the visualization or the analysis, to get there, you we really face difficult challenges because we have to go from the data, even though sometimes we have to go before having the data, like the data collection, the data structure, and those steps are already very difficult, but there are more human-computer interactions for the crowdsourcing interfaces or computer vision for the automatic tracking. But for the visualization part, it's also very challenging because you have all types of data structure. You have graphs, you have lots of data points, so you have scalability issues. So we really face many challenges. It also gives you some work to non-experts. As I said, I think everybody has a good idea of the sport. So, I mean, most popular sports rules. So if you work in this area, you get probably a broader audience. That's particularly useful when you want to get to collect some feedback on the visualizations. Using a sports data set might get you to a broader audience. And finally, there is also a growing number of careers in the sports analytics industry, because we've all heard of successful use of data analytics to improve teams' performance. So as I said, it's difficult because it addresses many challenges, and I'm going to detail that a little bit. So one of the main challenges is that all sports are different. They have their own rules, their special representation, and even if you take one sport based on the region or the level of its practice, then you get a different. It's sometimes different sports, so it's difficult to really analyze even one sport as a unique object. Like each sport or each way to practice it has its own data set or data structure. So it's difficult to have a unique visualization for all sports. It's really a fragmentation of different visualizations. Space. So the locations are very important to understand the context of the sport games. Space is about not only positions, but also relationships between the players between themselves, the players with his body parts, his accessories, the ball. So most of the data you get or you want to get about sport are spatial. And unfortunately, few public data sets at least have a spatial dimension. Sharing is difficult, not technically, but mostly because sport is a competition. So if you share your results with your opponent, and the opponent might understand either your strategy or your way of working, so you might get actually less efficient or less in terms of sports performance, because not only because you are not as good as you thought or better as you thought, but because your adversaries are getting better and they understand your strategy. Also, when you talk to sport analysts, if you find something that reveal the weakness of one of their team, they might ask you not eventually to share your results because it's, as I said, it's a weakness they don't want to reveal. And finally, data. So data, as I said earlier, already is the main challenge. Sports data are usually incomplete, messy, inconsistent. It's really difficult to find a good sports data set you are happy to work with. It's always either good events or good tracking data, but rarely both. And what you have on the right shows that it's also difficult to get like this good descriptive statistics of sports data. It's difficult to summarize either spatially because it's lots of code locations without events, but if you do statistics on the events, you like the spatial context. So we see that we always need to find the right balance between show some spatial information, show some events, but it's difficult to show just one. So here are some examples of data sets structure. So what we call data domains or data models. So it represents the basically what are the columns of databases. And as you can see, so that's something you find in probably all sports papers. This is on the top left. This is the ITTV's data model that basically explains both the rules of the table tennis games and also the names of the events and regions that are being used for to analyze games. Below is a sports data, soccer data model, where basically you have players that have locations, which is probably the easiest types of data sets, only coordinates. And when it comes to events, as you can see, you have a broad range of events. I think for this data set, we had probably up to 50 different events. And the yellow diagram shows another soccer data structure. And here I wanted to emphasize that depending on the data set you're going to use, you're going to have a different database model. Space is actually not as easy as I mentioned earlier with just y and x and y coordinates. So of course you have positions, but the positions need to be put in a special domain. That means you need to have an origin, and your position needs to be adapted to this origin. So that means when you plot your data on a visualization, and that's what we're gonna do later, you'll have to understand what's the origin, what's the orientation of the field. Is the field vertical, horizontal? And fields actually don't have the same properties. Like even in soccer, that's something that might surprise you, but there is all the soccer fields have different dimensions. So it might get an issue when you want to compare events, shots, or position or shot positions across countries or across time. You might not actually be able to do it because the coordinate system is a bit different. So you need to do some normalization, which might be a complex part of the visualization process. And here is so actually most of the data processing, sports data processing toolkits have like pitch backgrounds, and here this is the MPL soccer Python module that lets you to plot soccer data and have this nice XKCD background. So I don't know what can be used for, but at least you know it exists. I'm going to show you now a couple of examples of sports visualization. So here's probably my favorite one. It's the Court Vision sports basketball visualization. It shows all the field goal attempts during one season in the NBA. So you have thousands of shots, and each shot is represented as a dot. The color encores the distance to the basket. And here, even though it's just plotting data, of course it could be done differently, but at least here it already tells a story that people attempt 3 shots behind the 3 shot lines, and they rarely shoot at the basket right after the 3 shot line, which kind of makes sense. And you have also shots. Most of the shots are close to the basket, and you have this region here below the arc that doesn't have that much shot. So this was probably one of the visualization that really kicked off the the basketball visualization. It was published in 2012 by Kirk Goldsberry, and then there has been lots of variations of this visualization. Another type of visualization I also enjoy are the pitch control visualization. So pitch control visualization basically lets you grasp where space is available and where players can go. So if they receive the ball, they are not likely to have an opponent coming at them right away. So on this visualization, so on the top row, you have the video snapshots, and below are the corresponding speech control visualizations. So in red, you have Barcelona, and here the story is you have these players that goes backward. I think this is Iniesta goes backward because one of his teammates was progressing towards the goal with the ball. So here he got some empty space. And this visualization, as you can see here below, shows that if Iniesta gets the ball, then he will have some space to either control it or to run towards the goal. So that's basically the story of this visualization. So Iniesta got the ball and passed it, I think, to Suarez. So nice thing with pitch control visualization is they use space, background to encode an additional information that's compliant with the visualization above, which here it's an animated dot plot. So it just uses the background and it doesn't create visual clutter. Here is a density map of all Federer versus Murray shots, and here it basically shows all the positions that the ball from Federer went through when it was hit during the game. So here we have lines, and the lines are overlaid to each other, and you have this density visualization. So basically, it shows some probabilities where the ball might go through during the game. And finally, a tactical map visualization that shows the alignments of the different teammates. So we have all the defenders here, midfielders, and attackers. And it shows this encoding, so using some sort of graph, some connection encoding, it reveals if defenses are aligned. It also reveals the strategy of the lineup of the team. So here we have a 4-4-2 lineup, and it seems the team is keeping this lineup, and the way the team is also organized, it has a dense midfield. So we have seen some example, and usually what we try to do with a visualization domain, we try to organize examples using what we call design spaces. In the case of sports visualization, it's kind of tricky to do it because there are so many different sports, so many different audiences. I've tried to identify some sort of design space for not necessarily for sports visualization in general, but for sports visualization we're going to use in this tutorial. So and organized it in 2 dimensions to stay simple. So the first dimension is either we have events, so shots, ball hit that occurs during games. So those are the stars, and that's the leftmost part of the spectrum, and the rightmost is events with positions. Events with position is what we want to get as a data set, but unfortunately we don't always have such data set. And in between, you only have positions. So this is where I will put the two of the visualizations we've seen before. And the second dimension is related to the data processing we're going to do over those events and positions data sets, right? So it's basically data transformation. So you might think that's not necessarily very does not result into some very interesting visualization, but we will see that's actually what, especially when you work with spatial data, all those operations, they usually results in very meaningful visualization, because it's about space, and space provide context. So just by binning, deriving values like the speech control model, or connecting the players, we'll see that we'll get some interesting sports visualizations. So I haven't filled this space. Doesn't mean it's empty. Just I haven't put like so too many examples, just to focus on the few we've introduced before. So now we're going to talk a little bit about the tools and the sports data sets. So as the goal of this tutorial is for you to live with an experience of actually building a sports data visualization, we're gonna have to use some tools to fasten a little bit this process. So there are many possibilities. From my experience, there are lots of Python modules to get into sports data visualization or sports data analysis, and but it's we get the same situation as when we want to do a visualization in general using Python. It's great for data processing. It's great to scrap data, to enrich data, to do some machine learning. But when it comes to visualization, we usually only get static or animated visualization. I know now there are some interactive ways to do visualizations, but we won't have that much control and that much quality of rendering than if we were doing some JavaScript visualization. So I've put some lists of a list of modules you may want to look at. They are very complete. As I showed earlier, they already implement the background, like soccer pitch backgrounds, which is extremely convenient when you want to plot sports data. But my opinion is you might want to get into JavaScript and of course D3 to do some visualizations where you have more control on the rendering process, and you can create novel marks. Unfortunately, there is no D3 sports visualization. That's there are some JavaScript modules that help you to load sports data, but I haven't found any good either soccer or basket or any other sports visualization toolkits in JavaScript. Even though there exist some notebooks that explains how to create D3 soccer pitch and their background, but it's not that complete. And you have Tableau software and R modules. For Tableau, it's more about examples and list of contributions. With R, so I'm not that much familiar with R, but R is probably as equal as Python in terms of sports data analysis modules. It's incredibly rich to collect the data. It automatically gets the data from APIs. It has it has uniform data models, but as I said, I have the same argument than for Python. I think if you want to get into interactive and highly customizable visualizations, you have to go through JavaScript. And you have commercial products. Most of them are you have to pair, but there is this one, Metrica Sport, which is very very well designed to annotate visualizations on videos. So it basically takes videos as input. It does some computer vision to calculate the position of the cameras and the players, and then you can draw those distance or highlight players, and it's very, very neat. But still, it's a commercial product. The free version has limited number of features, and it has the limits of not being customizable. So how to get to sports? How to get sports data? So, as you may already know, there is not a lot of sports data sets. The ones that exist are usually limited or inconsistent. So you might think, okay, let's just get your own data. So people have done that in the past in a very, very efficient way, even though it was all manual. So people used to print score sheets so it's of course suited for event games, event sports like basketball, like baseball, where you have events, and it strongly relies on events. For tennis, you have those spreadsheets you can fill for tennis games. And even if you want to get started, you have the templates or Excel templates you can print and collect your own data. The only problem is that usually the spatial dimension is not very well accurate. You annotate using regions, so the division of the field or the pitch into main parts, and it's difficult to annotate the ball trajectories, those kind of things. So another way to annotate and get the data is using what's called annotation tools. You basically get you basically load pictures as inputs, and you draw bounding box, put labels to the bounding box. So here I have drawn, so bounding box is this rectangle. I've drawn over a soccer player, and I annotate with a label saying, oh, this is a person from this team and doing this action. And you do that for every single video frame. And videos usually are 25 or 50 frames per second. So if it takes, even though just a couple of seconds per frame, it's a huge, it requires a lot of time to annotate completely a video. But if you just need some samples, because you want to do machine learning, or you don't need a complete video, you can do it, and the output are usually in a structured way. So videos are not structured, it's just pixel, but the output will be structured. So values with names of as the key, using XML or JSON. And finally, there is computer vision. So computer vision is a huge domain. It's moving fast, so hopefully we might get soon some better sports data sets. Though it's a difficult process for many reasons. So first, it's usually a pipeline, so a series of steps from videos to the data. You have one of the steps are the code detection, so to get this from above view of the field. So whatever you detect, you will be able to put it in the right coordinate system. Then you need to detect the players, characterize the motions, classify, and make sure everything is correct. So you have some checks to do. There are some good systems, but it's difficult to apply them as a general purpose tool where you can put just any video and get the output you expect. It's usually designed specifically for some sports. But my opinion is that's probably the most promising way to get high quality, fine grained tracking data. Classification of movement might take a bit more time because it's even for humans, it's not easy to identify what are the movements, what are the types of motions, and so I don't know if we're gonna get to automatic movement detections, especially for sports like racket sports where the type of movement is very subtle. Finally, one of the other types of data set we might get is the so an example of data sets we actually got, and that's very complete. It's the SportsView basketball data set. It was collected back in 2015, 2016, only because the NBA decided to install a system of 6 high-speed cameras to record all the games and to have a very efficient tracking system. And they managed to get all the players' positions and the ball. And I think the ball is in 3D for more than 600 games. And this dataset is available, and that's what I've been working on in the past. It's very high quality. The only drawback, because we cannot get a perfect sport dataset, the only drawback is it's difficult to get the videos. So you do lots of like pitch control or shot statistics analysis, but you might want to get back to the video to check and or just enjoy the game because you've looked at abstract maps all the time, and getting videos is difficult. So, but still here we have good positions and for really complete season. Another example, I'm going to give you 2 other examples of good data sets because they are the ones that we're going to use in this tutorial. First one is the LastRow sample dataset. So LastRow the company has been collecting lots of data, and they share for free goals sequences for some Premier League games. So we have up to 19 goals scored by Liverpool, for instance, in 2019. So we have position of the players, not just the players with the ball, but really all the players plus the ball. And another interesting data set is the stats-bound data samples. Here we have we have events on players, but who have the ball, who own the ball. So it's not the position of all players; it's only the position of the player once the player gets the ball. So it doesn't look very fantastic data set, but actually the sports data analysis has been really exploring those data sets, and they've provided lots of data models, data metrics based on those data sets because they were recent. So on European soccer leagues, and well, probably lots of people were doing analysis, and it happened also a couple of years ago, so it's very recent. So we have as a conclusion for this first part, so I'm a bit in advance, so I will that's fine. I will take a bit more time to introduce the demo. So what we have seen so far is we have seen the general domain of applied sports visualization. We've seen some example of spatial visualization. We've seen data is a big issue, but though we have data sets that are sufficiently complete to work with. So the second part of this tutorial is gonna be a more like a hands-on approach. It's going to be about live coding. So I'm going to show you the data, and I'm going to show you some code. And my goal here is really to show you the process from the raw data that's been published to the actual visualization. So we're going to see two types of visualizations in two parts. So the first part will be on events data. So basically all the events that happen around the ball. So every time the ball was hit, an event was generated. And the second part will be about position data. So here we won't have events. We're just going to have the position of the players and the ball. The events data will be about the female World Cup semifinal. And the position data will be about a specific goal about the Liverpool team in the Premier League. So the first code demo we're going to do is what's called an event chart. Sorry. So an event chart is created using all the shots, all the events that, like the shots that occur during a game. And it's usually a way to show some distribution. So it's probably one of the first charts we build when we get the data. And then usually the process is to get into some interesting events. And here it's about soccer, so it's going to be about goal events. So sorry to spoil you the results, but it's been nearly 3 years, but the game ended up with a win of Sweden. So Sweden finished third of the Female World Cup 2019, and Sweden scored 2 goals against England. So how to build event charts? So first is we're going to look at the data. That's probably the very first thing you need to do. Once you get the data, once you have the data set available, so we assume data set is here, you just received it, and we're going to go through the data exploration process. So I'm going to use observable notebook to do the code demo. I don't know if everybody is familiar with such notebook, but it's very convenient to quickly load the data set, write visualizations in D3, either from scratch or using visualization modules like Vega or the one we're going to use, which is a recent visualization module called observable plots. So I'm going to start with I'm going to increase the font size. So I'm going to start with just naming the notebook, and I'm going to load the data. So the data is from an open data directory from StatsBomb. As you can see, there is a description. And what's interesting is the structure has is the following. We have competitions. So we have all the games that are listed with the metadata of the games, like the competition gender, the competition name, the season name. So this is what we call earlier metadata. So they are about the games, and this is what we use to pick the game we're gonna analyze. Usually, once you get to the files that are that contain the sports data, your file is named using some sort of competition ID or any other identifier, and we won't have any more access to those information because it's there, and you need to join the files to get your those metadata into your visualization. But we're not going to do it, but I just wanted to show you that was there. So to get to our event data, we need to go to the events directory. And here we're going to have a lot of games. So we're not going to take all the games. One file is one game. And I think files are a nice way to organize data in sports, because you can look at the files. Usually the data set, they are not structured in a way that all the columns are filled. Usually observations like rows, they have different attributes between each other. So this is why those JSON files are a good way to structure the sports data set. So I'm going to load this file, which is the game we're interested in. And I'm going to load it into the notebook. I could explore it using the text version, but I think it's better once it's loaded into a notebook. So we have more than 3,000 rows, like more than, what we might guess is at least more than 3,000 events. And actually, if I look at the first item, so there are lots of indexes to join this file to the other one. But what I'm seeing here is that this event has a duration of time 0. So it sounds a bit suspect. It starts at 0. And actually, this is not a play event. This is actually a lineup event. So this is where in your data set, you get the lineup. The lineup is the organization of the team before the referee kicks off the game. So that's something to deal with. The nice thing, at least, is we had one file that was a package of everything, but now we need to split this file into what here we could call metadata again. So those lineups were not in the other metadata file, so it's as a kind of header for this events dataset. We also have tactics. So this is tactics of the other team, and so on. So I'm going to load. So I'm going to name this dataset row. I'm going to generate the table. So it's a bit better to look at the dataset with the table. So my second observation is, so here we still have those like time 0 events, so probably more metadata. And if I scroll down, I have events with duration, no duration. But what's a bit annoying is those objects are actually nested objects in the JSON file. So I don't have a flat structure. I have some sort of hierarchy, which might be there for a reason, but it's difficult to explore with a table. And I have positions. So I'm happy I have positions, and as you see, I have many events. So what's the next step? So the next step is to type the data sets, because we have lots of numbers. So I'm going to use D3 prototype. Okay. And I'm going to create a copy of this data set because I need to have I need to create new attributes, and eventually I need to also filter a bit this file. So actually, I'm going to start with the filtering. So what I want to have, I want to focus on positional events. So I will filter out all the events that don't have locations. So I'm just going to remove events without location. Okay. So if the location is not defined, then it would be the row would be removed. So I have slightly less rows. yeah, that 25 rows have been removed. And now I want to derive some attributes. So I'm gonna generate a new. I'm gonna okay, so I'm gonna create some so I want to derive some and reorganize the attributes. So here, what was a bit annoying was the position. The position was not in 2 columns; it was one object. So I'm gonna create an X attribute, which from the did location 0. So now I have events with position, so only X. So I'm going to continue with right. With Y events. Okay, so now I have my 2 coordinates. What was also annoying was the players, they have a name. So I'm not gonna take the first items. Like here, I see the players, they have a name, but it's nested. So I'm gonna extract the player name. And so on. So as you can see now, I have a flat data structure. It's going to be way easier afterwards to map to the visualization and to do some grouping. And I'm going to do that for the team name. For the position ID. Okay, so I have coordinates and team names. So let's just do a first visualization. So I'm going to use the plots, library, which is very convenient to plot this type of data because it has a very nice way of defining the marks as a list, and I'm going to add a dot mark using my data sets and a list of mapping of this mark. So I'm going to use the dot mark with X coordinates, X and Y coordinates, and so on. And here it is. So it's close to random noise, and it's really difficult to make sense of. So what do we do? And actually that's close to what we usually where we usually are when we plot visualization. So I'm gonna go back to so this visualization on the bottom right. That happened. That's the visualization that's generated with a huge data set I received from a company, and somehow so this is a tracking data set, so it was more like finer grain, and I was happy that I saw the boundaries of the field, and I saw the goalkeepers that stayed in their goals, but it's pretty difficult to make sense of. So now let's do some more encoding. First, what I really think and what's really specific to sports visualization is to add a background. Like it sounds like a very simple step, but just plotting the perimeter of the field might actually help. And hopefully observable plot has a image mark, and to which we should give a data. So we need to load the logic of observable makes it that you need to load the image as a data set. So we're gonna load it as an attachment to the notebook. And hopefully I always have a soccer pitch on my desktop, so it was there. So now it's attached to my notebook. So I'm gonna load it as a JavaScript cell and file attachment. So now I have the URL of my pitch. And actually, I need to create a data set. I'm gonna call it. So I'm just creating a small dictionary with this this URL, so it will make my life easier to load it as a data set here. And I need to set some coordinates and a source, which is the URL. Okay, so you cannot see anything, but it actually it's here, and it seems it's not correctly loaded. I need to add so here it's my background is here, and now is the step where I need to understand my data coordinate system. And from experience, it really takes a lot of time to understand the coordinate systems and make sure your data fit to the background image. So I've done that for this data set. So I'm gonna copy and paste some variables for the plot. So I've added specific width and height for the chart, and now I'm gonna add some specific x and y for the and dimension for the background image. Okay. So we could have spent probably 10 to 15 minutes together to load the background, make sure it fits to the data set. So I've skipped this step, but I've just all the parameters I needed to load the background are the dimension of my plots and the dimension of the background image I loaded. So the image is some sort of mark with its own data set. Here it's just unique and static, and the dots are an overlay over this mark. And okay, so now we don't really see much of a pattern. It's not like basketball where we could see some patterns with the landmarks of the field, but here it's still, I think it needs some more investigation. One way to make sense and eventually to reveal some pattern, because here we saw some small changes, but maybe there are some regional patterns, is to go to the second step, is to do some binning. What I put in my space here was the binning, which basically a spatial grouping of locations. So might remove some noise and reveal some patterns. So I'm going to go back to the slide. So binning is something that's well documented in many libraries. So I'm not going to go through all the binning step, but the binning algorithms. But basically, the idea is to group a continuous scale into a category. Is to map a continuous scale into a categorical one, according to some bins, so some intervals. It can be achieved on a one-dimensional scale or two-dimensional one, and the observable has a nice plot bin transform I'm going to use to bin those data. So I'm going to keep using observable plots for that. And the binning is in two steps. So the first one is to create the rectangle mark from our data set, because the result of the binning will be rectangles with colors. But still, I need to do some transformation on my data set. So I need to use the bin function. And the bin will create a new attribute called the count, which is the number of items per rectangle. And now I need to define the position of my rectangles, so which are X, Y, okay. Not a great color scheme, so I'm gonna use a different one. So because I think it's a categorical color scheme, and I'm gonna use okay. So here's a better color scheme, and actually it reveals a bit more of some more patterns. As we see, there are like on one side, there has been lots of events, like high density of events, and it's relatively sparse in the middle, but on the sides there have been and in the middle there have been many events. Still, we put all the events in the same space, and they are not all similar. So that's actually the second step we're going to do, is we're going to now break down by events and even break down by players, because the players, they have different roles, and an event at a given position doesn't mean the same thing if it's triggered by a forward or defender. Like if a defender scores a goal, that's something that's unexpected, that happens, that's highly unexpected. So this is what we probably want to learn from the data. So that's going to be the second step of this this visualization, is now to break down the visualization by players and events. So what we need to do is to get, and to do so, we're going to do it using by implementing some interaction. We want to let the user to eventually apply some filters, and after that we'll see a variation of then using interaction. So how to add interaction in this with this chart? So first we need to list all the events and all the players. So we're gonna create a list of players, which will be a set, so a list of unique items from the from the data set. I'm gonna so I don't want events without locations, and now I'm gonna get the list of all players by name. Okay. And I have a set, and I want a list. Okay. Okay, so now I have a list. So why do I want a list? It's because you'll see it's the what we can use as input for our widget. I talked about interaction, and I should have said I'm going to use widgets, so drop downs, menus, or checkboxes. Here for the players, I'm going to use let's use a drop down menu. So I have my list of players, and I'm gonna get the variable from the selected player. And now I'm just gonna filter these charts with the selected player. I'm gonna comment the bin, so we'll see the filter events a bit better. And now here I filter the okay. And here is so an interactive version of the chart. So as you can see, the events now they are filtered by player. So we have less events. But you've also seen that we have some issues like this one. This is also a bit of a problem when we have events that are that only occur locally. They don't occur on the whole field. So that means the way we've designed this chart was to center on all the events, which was fine when we had a full game because events occur everywhere. But now we need to make sure if we only have a subset of the events that are locally distributed to the defense or the attack, then they we still show the complete field. So I need to add some parameters to the scales, and I'm gonna say that the domain. So basically, the value interval the plot is gonna take to define the event's position is going to be the full interval from the full data set, and not just from the subsets of the player's event. So I've done that for X, and now I'm doing that for Y. So observer plot was designed like really to be compliant with D3. So if you know some D3, it's those parameters are typical to they are familiar to you. So now we have this the same plot, but now it's we have stabilized it. So now whatever you select as a subset, it's always represented on the full pitch. And so here you can see that this player seems to be a so I don't recall if she's a forward or defender, but you see that the region is very limited. Okay, so we filter by by players. Now let's do some events selection. So we're gonna do the same process. We're gonna create a list of events. And I need to filter by events. Okay. Here are all the events types. And I'm gonna use them as a widget list. So this time we'll be able to select multiple events. We could have done that for the players, and we are going to use a checkbox list. So now we have we can select the shots, the errors. It's not connected yet to the chart, so this is what we're going to do. And we're gonna do that, and then we're gonna go on the break. So we're gonna add filter, and here it's actually very simple. We need now to add another condition. Here we want the dot type name. So here we have records with events, and we want this type name to eventually be to check if it's in the list of selected events. So we want to know if it has an index above -1. Okay. So now what do we have here? So we have selected one player, and we have selected none of those shot types. So just select one of them. Right, that must be. It was selected event. Okay. So I'm going to check which were the selected events. So 10 are selected, okay. And I want to make sure the one selected is not 10. Okay, I'm going to pick another. I'm going to check if I have the right. Okay, so actually I forgot to get the. Okay. Okay, so now it works. So I uncheck all the events. So now if I'm interested by the shots. So here I see that Francesca Kirby had one shot, and I'm sure we're gonna go back to the statistics, and we see that we have one goal by Asilani. So actually, Francesca Kirby is the one who scored for England. So that's her shot, which outcome I guess was positive. That means it was a goal, and so I remove it. So now I looked at Asilani. And there is another shot that led to a goal. Jacobson. Okay, here are our shots. Okay, so what we've done, we have these event maps, we have those filters, but still we probably need lots of interaction to really grasp the dataset distributions. So this is why in the second part of this workshop, we're going to get to small multiples. So I'll be back in 25 minutes because I'm running a bit late. So I'll be back at 3:45. So see you in 25 minutes.
For over 131 years, the University of Oklahoma has been making an impact. It is a legacy of excellence, a legacy defined by courage and determination, a legacy of champions, both on and off the field. And we're not done yet. From big wins to bigger discoveries, we're advancing Oklahoma, the nation, and the world. Because at the University of Oklahoma, we change lives.
Hello, my name is Peter Wonka, and I will present an overview of the Visual Computing Center at KAUST, also called VCC. The VCC currently has 9 faculty members who publish academic research in the areas of computer vision, computer graphics, visualization, and machine learning. We strive for academic excellence, as evidenced by high rankings from websites, such as CS Rankings, that track publications in the best conferences in different subject areas. VCC research is supported by various core labs. The KAUST Supercomputing Laboratory provides access to supercomputing and a GPU cluster. The Visualization Core Lab maintains visualization facilities and VR equipment. Computational imaging is supported through devices for industrial tomography, microscopy, or cryo-EM. Now, let me show you around at our center. The Visual Computing Center is located in one of 5 research buildings that houses faculty from computer science, mathematics, and electrical engineering. The research buildings are connected by a major walkway, the spine. Along the spine are various shops selling items to support the daily research activities. Most importantly, coffee. Now, we're entering the building on the 2nd floor, where the VCC is located. We are flying around to take a look at the arrangement of offices and cubicles where staff, students, postdocs, research scientists, and faculty work. The posters on the hallway highlight successful research projects from the past. Several meeting rooms can be used for group meetings, lectures, or project discussions. Our faculty teach a wide range of courses in visual computing. Due to the excellent professor-student ratio at KAUST, some specialized courses can even be taught in faculty offices. our research can also directly be applied to such a video stream, for instance, for activity recognition. Or depth estimation. One part of the VCC is dedicated to the Computational Imaging Lab, which allows for optical setups and the development of combined optical and computational imaging systems. VCC facilities are directly adjacent to facilities of the Visualization Core Lab. For example, the Next Cave. And the large display wall shown here. We would like to highlight the VCC startup company FalconViz that took the drone footage for this video. This concludes our presentation of the VCC. Our members thank you for stopping by and visiting with us. We hope to welcome you in person in the future.
From desktops to data centers, CompuServe to the cloud, the orderly march of progress. Yeah, no. Progress only looks orderly after it's happened. Before it's happened, it's problem after problem after whose idea was this anyway? Unworkable, unfeasible, impractical, impossible. But then you put your head down and you work the problem until answers emerge. New solutions that power you through the next problem, and the next one, and the next one, and the next one, until you get to greener buildings, cleaner cars, smarter factories, bigger blockbusters, interplanetary landers, walking cars. 4 decades of solutions. But it's always been about one thing: finding new ways past whatever problem stands in our way. And we're restless to do more. And that's why we love problems. Because we know when you combine the right solutions, when you merge fields, and converge the technologies no one else can, what's wrong with right now can become what's better about what's next. It's about opportunities, not obstacles. It's about unleashing your talent, not restraining it. It's about unlocking insights in your data. It's about making the things that actually make the world a better place. So let's get out there and do just that. Let's blur boundaries. Let's reinvent rules. Let's redraw the lines that define your talent, your business, your entire ecosystem. Let's go do what doers love to do. Let's not wait for progress. Let's make it. Autodesk it.
For over 131 years, the University of Oklahoma has been making an impact. It is a legacy of excellence, a legacy defined by courage and determination, a legacy of champions, both on and off the field. And we're not done yet. From big wins to bigger discoveries, we're advancing Oklahoma, the nation, and the world. Because at the University of Oklahoma, we change lives.
Hello, my name is Peter Wonka, and I will present an overview of the Visual Computing Center at KAUST, also called VCC. The VCC currently has 9 faculty members who publish academic research in the areas of computer vision, computer graphics, visualization, and machine learning. We strive for academic excellence, as evidenced by high rankings from websites, such as CS Rankings, that track publications in the best conferences in different subject areas. VCC research is supported by various core labs. The KAUST Supercomputing Laboratory provides access to supercomputing and a GPU cluster. The Visualization Core Lab maintains visualization facilities and VR equipment. Computational imaging is supported through devices for industrial tomography, microscopy, or cryo-EM. Now, let me show you around at our center. The Visual Computing Center is located in one of 5 research buildings that houses faculty from computer science, mathematics, and electrical engineering.